everyone, my name is Gladtha Senduk, student number identification 19 20 90 53, Civil Engineering, Manado State University. This presentation material is taken from a book, Concise Environment Engineering. And now, I will presentation chapter 7 till 9. Okay. 7. Water pollution. Water pollution refers to the introduction of a substance to the environment use of a resource or degradation of the health of humans, wildlife, or ecosystem. Pollution may be caused by point sources at stationary location, such as an effluent pipe, or non-point sources, also called diffuse sources, such as land runoff and the atmosphere. The mass flux of a pollutant is expressed as a lot in mass per unit time. 7.1 Main pollutants. Organic waste. Organic matters in water are composed of organic compounds. Generally, most carbon-containing compounds are organic, excluding steel and simple oxides of carbon. Organic compounds include natural compounds, i.e., living organisms, which are capable of decay, and synthetic compounds, i.e., plastic, which may be biodegradable. Many organic matters are synthetic and not biodegradable. Term refractory organic matters. They include pesticides, detergents, and petroleum hydrocarbons. Some pesticides and other refractory organic are the principal agent responsible for the decline of certain ecosystem species and are the threats to human health. Suspended solids. Solids in water may come from mining activities, river dredging, construction, i.e. road and bridge, and soil erosion. Next, nutrients. Nutrients, nitrogen, phosphorus, sulfur, in water encourage plant, usually in the form of algae. Those nutrients come from domestic, industrial, and agricultural waste. Diffuse pollution from agricultural waste is a major source of nutrient, especially nitrogen. Nutrient-enriched water is more productive with excessive biological activities, and water quality is usually significantly degraded, i.e. eutrophication. Next, thermal pollution. Industrial cooling processes, i.e. fossil and nuclear power plants, discharge heated water into water body with effects on reduced solubility of O2 and altered speed of chemical reaction. Thermal pollution changes the natural temperature regime of water system and the affected ecosystem could be stressed. Some aquatic species may die or are forced to relocate. Next, toxic metals. They are metals that form poisonous soluble compounds. Toxicity is linked with solubility and is directly proportional to its ability to cause environmental damage. Next, pathogens and carcinogens. Those are disease-causing microorganisms or cancer-causing substances include bacteria, protozoa, dioxins, etc. Domestic wastewater is responsible for many of the pathogens, and industrial and agricultural waste are the usual sources for carcinogens. Next, radioactive contamination. In the natural world, there is always radiation being emitted from radionuclides. Radioactive contamination refers to unintended or undesirable presence of radioactive substance in water, usually from the leakage of stored radioactive material or release from nuclear power plant accidents, etc. Next, 7.2 Water pollution indicators. The indicators on water pollution are in three categorical: physical, temperature, turbidity, total suspended or dissolved solids. Chemical, pH, dissolved oxygen, COD, BOD, pesticides, metals. And biological, EPT index, strain biotic index, indicators. Most of them have been explained already in the book, and only a few indicators are further explained here. Oxygen saturation. The maximum amount of oxygen dissolved in water at a given temperature is called the saturation concentration. It is determined by Henry law and varies from 40.6 mg O2 per liter at 0 degrees Celsius to 7.6 mg O2 per liter at 30 degrees Celsius. As a result, fish with high oxygen demand prefer cold water. Next, biochemical oxygen demand (BOD) is the amount of oxygen required by microorganisms to break down inorganic matters. It is used as an indicator of organic pollution of water. Next, typical BOD 5 values. Pristine water up to 1 mg per liter. Moderately polluted water 2 to 8 mg per liter. Treat sewage by 3 stages up to 20 mg per liter. And treat sewage up 600 mg per liter in Europe and 200 mg per liter in USA due to dilution from more water consumption. Next, chemical oxygen demand (COD) measures organic matters which are both biodegradable and non-biodegradable. Hence, it covers a more broad spectrum of organic matters. As a result, the COD in water sample is always higher than the BOD. Next, biological indicators are useful to get a general reading of water quality without the high cost of lab-scale analysis. Various are used to represent the states of macroinvertebrates. They are in two types. First, pollution indices, existence of or absence of indicator species. 2. Diversity indices, to indicate the overall effect of all pollution. However, biological indices are not always reliable. Factors other than pollution can affect the biological indices. Absence of some species may reflect its normal life cycle, and quantitative sampling of biodiversity is difficult. Okay, 7.3 Wastewater treatment. Wastewater treatment plants receive inflows from domestic, commercial, agricultural, and industrial users. Stormwater runoff and infiltration. Industrial waste may contain heavy metals, radioactive materials, refractory organics, which may be treated on site following specific guidelines. Domestic wastewater is commonly treated in municipal wastewater treatment plants. A main purpose of wastewater treatment is to control pollution of a receiving water body, river, lake, groundwater, sea. To design an effective treatment system, it is important to 1. Identify the characteristics of raw wastewater. 2. Set treatment objective. 3. Integrate unit treatment operation. 4. Assess the system in view of green engineering, life cycle thinking, and sustainability. Treatment units include: first, pre-treatment, to remove coarse solids using screening, to remove grit using grit scumbers, to remove fats and greases using flotation, and to maintain a stable flow using an equalization basin. Next, primary treatment, to remove solids through gravity setting using sedimentation. Tanks to removal rates are 60% suspended solid, 30% BOD, and 20% phosphorus. Next, secondary treatment, to remove dissolved organic matters using microorganisms. Biological treatment. Next, tertiary treatment, mainly to remove nutrients such as nitrogen and phosphorus. Next, disinfection, to remove pathogenic microorganisms using ozone, chlorine, ultraviolet light, or sodium hypochlorite. Next, sludge treatment, to treat and store the sludge from the treatment processes. Next, disposal. The water sludge may be buried in a landfill. Carbon sequestration, incinerate with a potential problem in air pollution. Apply to agricultural land as fertilizer. Next, natural treatment system. Wetlands are an alternative wastewater treatment method. Next, septic tanks. A septic tank is a small-scale sewage treatment system in areas with no connection to main sewage pipe, usually in suburbs, and small towns as well as rural areas. Next, 7.4 Water Quality Modeling. Water quality models are used to analyze environmental systems and predict water quality changes due to modification and catchments and wastewater treatment plants. The prediction provides a basis for engineers to carry out economic analysis to evaluate various options to improve the environment. Water quality models are based on 1. The law of conservation of mass. Material transport into and out of the control volume as a physical process. And 2. The change of substance in the control volume, transformation of the substance due to biological and or chemical processes. Material transport refers to the movement of the substance from one point to another, which involves adhesion, movement with the fluid, and diffusion or dispersion, spread in the fluid due to differences in concentration. The following water quality models are widely used: aqueducts, basins, K, Sparrow, SWMM, WASP. First, aqueducts. Linking water quality and aquatic life, supported by EPA. Next, basins. Better assessment science integrating point and non-point sources, supported by EPA. Next, K, river and stream water quality model, supported by EPA. Next, Sparrow, developed by USGS, a surface water quality modeling tool for the regional interpretation of water quality monitoring data. Next, SWMM, Stormwater Management Model, supported by EPA. Next, WASP, Water Quality Analysis Simulation Program, supported by EPA. 7.5 Water Quality Standards for Pollution Management. Water pollution is usually managed by following water quality standards. Water quality standards are established by legal to define the level of pollutants allowed in a water system. There are three types of standards: receiving water standard and effluent standard. Receiving water standards refers to water quality standards for receiving water bodies, rivers, lake, seawaters. And effluent standards refers to the quality of effluents discharged to receiving water. The aim of both types of standards is to achieve the desired quality of a water system. The receiving water standard considers the use of the water system, swimming, irrigation, drinking, industry. Effluent standards set the required maximum pollutant concentration to be achieved or degrees of treatment required before discharge. Both standards are regulated and should be met. Water quality standard must be reasonable so that discharge should be able to achieve the standard through the available technology. 8. Solid waste management. Solid waste are defined as unwanted materials that are no longer of value to their owners, albeit they may be still of value to other parties. They are generated from various human and animal activities. Each year, billions of tons of solid waste are generated which are in need of proper treatment. Improper management of solid waste are directed adverse effect on human health and the environment, e.g., polluting rivers and groundwater sources and generation full air. 8.1 Sources and composition. The information on waste composition and generation rate is important for proper planning, treatment, and disposal of solid waste. Some solid waste, e.g., industrial, agricultural, and mining, are managed by the waste producer. In this chapter, the focus is on the municipal solid waste (MSW), which include residential, commercial, institutional, construction, and demolition. Another way to classify waste is to divide them into biodegradable, spoiled food, green waste, recyclable, paper, glass bottle, cans, inert, construction and demolition waste, electrical and electronic, TVs, computers, screens, etc., composite waste, waste clothes, Tetra Packs, waste plastics such as toys, hazardous paints, chemicals, fluorescents, tubes, spray cans, fertilizer, toxic pesticides, herbicides, fungicides, medical, pharmaceutical drugs. 8.2 Waste properties. Solid waste management options depend on physical and chemical characteristics of the waste. Waste generation rates are expressed in mass unit, i.g., kilogram per cube meters, instead of volume units. This is because waste densities are vary greatly among the waste with different compaction at different stages in the waste system: collection, storage, and disposal. The information on waste moisture content is used to derive dry mass of the received waste. In addition, for energy recovery design, it is important to know the energy content in waste. Plastic and paper have high energy content and low moisture content. In contrast, garden wastes are less productive in energy release due to their high moisture content. 8.3 Solid waste system. 8.3.1 Storage, collection, and transport. For this part of the waste system typically accounts for 40 to 80% of the total cost. For residential waste, the most common collection method is curbside. The wastes are usually segregated into different containers according to waste type: food, garden waste, recyclable. 8.3.2 Recycling. Recycling is to convert waste into new products. It can reduce the consumption of fresh raw materials. Recyclable materials include glass, paper, metals, plastic, textile, and electronics. Energy usage, air pollution from incineration, and water pollution from landfill. Successful recycling requires careful consideration of the processing capacity of the markets for the recycled goods, i.e., a potential demand for the recycled products. If neither of them exists, recycling is incomplete and in fact only collection. The cost benefit of recycling is complex. Economically, a major benefit is the reduced landfill cost. Other benefits can be worked out by comparing the market cost of recyclable material to the cost of new raw materials. 8.3.3 Composting. Composting is a microbial process used to treat biodegradable waste. This is similar to aerobic wastewater treatment. Composting has several purposes. 1. To reduce waste mass. 2. To reduce pollution potential. 3. To destroy pathogens. And 4. To produce compost as nutrient for gardens, landscaping, and agricultural organic farming. 8.3.4 Incineration. Incineration, waste to energy recovery, is a process to liberate the energy in waste by combustion. This is suitable for waste with high energy content, low moisture content, and low ash content, which include paper, plastics, textiles, rubber, leather, and wood. Incineration produces 2 solid byproducts, bottom ash, unburned waste, and fly ash suspended particulate matter. There are 6 commonly used incineration systems. 1. Mass burn for unsegregated solid waste. 2. Modular, small incinerators for specific waste such as medical waste. 3. Refuse-derived fuel, energy-rich waste as fuel to power plants. 4. Co-incineration to combine with production waste. 5. Hazardous waste, pathogens and toxins destroyed by high temperature. And 6. Cement kilns as fuel for cement production. 8.3.5 Landfill. A landfill site is a site for the disposal of solid waste by burial. This is the oldest form of waste treatment and the most common method for waste disposal in many places of the world. In a landfill, waste are packaged into solid form and covered to insulate them from water and air, usually every day with layers of soil. Leachate is a liquid drained from the landfill as a contaminated wastewater. In a new landfill with oxygen still available, organic matters decompose and carbon dioxide is produced. As time goes by, the remaining oxygen is consumed, and an aerobic condition leads to the production of methane gas. 8.3.6 Alternative technologies. In addition to the aforementioned traditional technologies, many new approaches are undergoing development. They include anaerobic digestion, alcohol or ethanol production, bio-drying, gasification, in-vessel composting, mechanical biological treatment, mechanical heat treatment, plasma arc waste disposal, pyrolysis, tunnel composting, UISB applied to solid waste, and waste autoclave. 8.4 Solid waste management. The combination of different components should be considered as a whole in a holistic way to serve the needs of the current and future generation. Good policy should be developed by analyzing policy options with assessment in cost and benefits, risk and unintended effects. The priority in a waste management policy is to reduce the waste and followed by reuse and recycle, the 3Rs. The 3Rs are expanded in Europe into a waste hierarchy: reduce, reuse, recycle, recovery, and disposal. 9. Air pollution. The Earth is surrounded by gas called air, which form the atmosphere. The atmosphere is a complex dynamic natural system essential to support life on the Earth. The air interacts with water and land. Acid rain falling on the ground is a result of air pollution. Many pollutants such as particulate matters, heavy metals, and ozone are able to influence water quality and ecosystem function. On the other hand, polluted rivers or lakes or sewage systems can cause air pollution in their surrounding areas. Therefore, it is important for a water engineer to understand the air and its related quality issues, and vice versa for an air quality engineer to understand water pollution. 9.1 Composition of air. The composition of dry air is listed in Table Composition of Dry Air by NOAA 2012. This table changes with the time. IG CO2 concentration has been increased with time. Air also normally contains water vapor, variable about 1% till 4% at surface. Dust, pollen, spores, sea, spray, volcanic ash, carbon dioxide, methane, nitrous oxide, and ozone. The air density at sea level is 1.2 kg per cubic meter, and it decreases with the increasing height. 9.2 Structure of the atmosphere. The Earth's atmosphere had distinctive layer with a total mass of 5 times 10 to the power of 18 kg. 3/4 of which is within the bottom 11 kilometers. The atmosphere becomes progressively thinner with altitude without a bird boundary. However, the Kármán line at 100 km above the Earth's sea level is commonly used as the boundary between the atmosphere and outer space. Beyond the altitude, the atmosphere becomes too thin to provide sufficient aerodynamic lift to support any aeronautical vehicles within the orbital speed of the Earth. The atmosphere is divided into several layers based on temperature profiles. First, troposphere. It ranges from 9 km at the poles to 17 km at the equators. It varies with seasons as well. Next, stratosphere. It extends from the tropopause to top of the troposphere to about 50 km. Next, mesosphere. This is from 50 km to 80 km with its temperature decreasing in height. Next, thermosphere. It ranges from 80 km to 350 till 100 km. It varies with solar activities. 9.3 Transport of air. The movement of air is divided into categories: the outdoor environment, ambient air, and indoor environment. First, global transport. Among the layers of the atmosphere, the two layers near the Earth's surface are more relevant to air pollution. Next, regional transport. High and low air pressures dominate regional air transport. Next, local transport. Due to the different temperature between land and sea in the coastal area, the wind direction changes during the morning and evening. Next, indoor air. Indoor air quality has a significant impact on human health. Design of ventilation system in a building influence temperature, humidity, and pollutant movement. 9.4 Air pollutants. Air pollution is the introduction of a substance, i.e. pollutants, in the air harmful to human and the environment, which may be natural, e.g. volcano eruption, or man-made. Pollutants can be solid, liquid, or gases. Major pollutants include: first, nitrogen dioxide. This is a reddish-brown toxic gas with a characteristic sharp, biting odor. Next, sulfur dioxide. Since coal and petroleum often contain sulfur, their combustion generates sulfur dioxide. Next, particulate matters. It refers to fine particles, solid or liquid, with diameter of 10 micrometers or less, which can be either man-made or natural. Next, ground-level ozone. It is produced by complex chemical reaction driven by sunlight. Next, carbon monoxide. It is produced from incomplete combustion of fuels and vehicular exhaust, is a major source of carbon monoxide. 9.5 Emission estimation and control. Emission is the amount of pollutant a source releases into the air. Emission rate is expressed as mass per time, such as gram per second, kilogram per day, or ton per year. Emission rate and pollution composition can change with time. Air pollutants are sourced from four main types. 1. Point source. A single, identifiable source of air pollutants emission, such as a single furnace. 2. Line source. One-dimensional source of air pollutant emission, such as a line of vehicles on a road. 3. Area source. A two-dimensional source of diffuse air pollutants emission, such as forest fire and landfill. And 4. Volume source. A three-dimensional source of diffuse air pollutants emission, usually found in oil refineries. They may also be divided as stationary and mobile, i.e. cars. There are 5 methods to quantify air pollutants emission. 1. Direct measurement, either stationary sensor or mobile sensor. 2. Mass balance, an indirect way by the conservation of mass from the difference between the measured inflow and outflow in a system. 3. Process modeling by mathematical modeling of physical and chemical process. 4. Emission factors modeling. Emission factors is the ratio of emission of pollutant source intensity and can be found in the published manual. The source intensity, such as kilogram per day times its relevant emission factor to derive the estimate emission rate. 5. Expert judgment, subjective estimation by express and knowledge. The reliability and cost are ranked from high to low, with the method 1 to 5, i.e. method 1 is the most reliable and most costly, and method 5 is the least costly and least reliable. There are 5 options to control air pollution. 1. Prevention, green chemistry, green engineering. 2. Regulatory solution, permit for allowable emission, monitoring. 3. Market solution, a total allowable emission cap is set and emission allowances can be traded in the market. 4. Voluntary solution, voluntary emission reduction by individuals, communities, and firms encouraged by easy access for air quality information. And 5. Emission control technologies, thermal oxidizer, to oxidize pollutant using high temperature in a similar way to incinerators absorption by passing pollute air through water-soaked media in a similar way to a smoke water pipe. Biofilter filled with a biological medium for the polluted air to be passed through the interate with the attached microorganisms, and particular emission control technologies such as cyclone, scrubber, backhouse, and electrostatic precipitator. Next, 9.6. Air quality modeling and forecasting. Air quality is modeling by air dispersion model, also called atmospheric diffusion model, air quality model, or air pollution dispersion model. A set of mathematical equations, physical and chemical process of air and its pollution is solved by numerical methods on modern computer. The dispersion model is used to estimate or predict the downwind concentration of air pollution emitted from various sources. Air dispersion model can be used by government agencies to determine whether an existing or new industrial plant will be compliant with the relevant air quality standards. They are also used by public safety organizations for air quality forecasting or scenario setting, which is important especially for emergency planning and operation of accidental chemical release, i.e. evacuation or sheltering for persons in the downwind direction. A typical air dispersion model requires information on 1. Meteorological condition, wind speed and direction, atmospheric turbulence, ambient air temperature, the height of the bottom of any inversion aloft that may be present, cloud cover, and solar radiation. 2. Pollution source. The concentration or quantity of pollutant is emission or accident release, temperature of the material, source location and height, type of source. 3. Terrain. Elevation at the source location and at the receptor location, land use or land cover information. Thank you.